Welcome to Chemistry at Honega High School. I'm Brian Brown, and today we'll be looking at our sixth set of notes dealing with quantum mechanics and the electron. Now, today we're going to start a couple of days of looking at electron configurations. Now, electron configuration would be a method of describing the locations of the electrons inside an atom. Now, they can be very detailed and involving all of the quantum information to be very brief. And what we're going to look at is four different types of notations. Now, the first two are the two that we're going to look at today, and we're going to use what's known as an Aufbau chart to help us do these two. And then on the second day of notes dealing with electron configurations, we're going to do these two electron configurations. Noble gas, which is sometimes called shorthand configuration, although I prefer noble gas because it's more descriptive, and then the electron dot, which is not in your book. It actually comes in a later chapter, but it makes sense to get to that level with the electron now. And really what's happening is with orbital diagrams, we have tons of information, but if we don't need that much work is not worth it. So then we go to an electron configuration notation, which is a slightly abbreviated form. Well, if that has too much information, maybe a slightly abbreviated version of that would give us enough. And then finally, if we get rid of all of the excess information and just keep the bare minimum, what would that look like? So each of these is going to be an abbreviation of the last. So to really understand each of them, you need to understand the previous one as well. Now, there are three fundamental rules we're going to use in writing electron configurations. First one is the most important. It's called the Aufbau principle. Electrons enter orbitals of lowest energy first. So we fill orbitals from the ground floor up, the lowest energy first. And that's known as the Aufbau principle. So when we think about what we talked about with our different sublevels and levels, this should be a picture of the first four energy levels. First, we just had the S, and there was only one orientation. So each dash represents an orbital. On the second, we had two different sublevels. Remember, N tells you the number of sublevels, so second level, two sublevels. And N squared would tell you how many total orbitals. Notice we have the one S and we have three P's, total of 4. Then we got to the third, we should have a total of 9 on our three sublevels. So 1s, 3p's, and 5d's. And we get to a fourth, we would have a total of 4 squared or 16. 1, 3, 5, and 7 for our f's. Now, if you really think about it, it's not that bad. And if only the atom were that way, things would be very, very, very easy and beautiful. But here's the problem. This is the actual order in which they fill. Yes, we've got the 1s first. And then after that, we've got the 2s, and then the 2p, and then the 3s, and then the 3p. But notice before we get to the 3d, we hit the 4s. And before we hit the 4d, we hit the 5s. And before we hit the fourth level s, we actually hit the sixth level s and the fifth level p. So really what it comes down to is, if we want to describe the electrons, we've got to remember this. So how in the world can you remember this? Well, we're going to end up looking at a couple of different techniques. And don't despair, it's going to be a lot easier than you think. The first one we're going to look at is what's known as an Aufbau chart. This is an example of mnemonic aid. It's just a memory aid that helps us remember what comes next. Now, think about our apartment building. First floor we had the S, second floor we had the S and P, third floor we had the S, P, and D, fourth S, P, D, and F, and so on. Now, we're going to modify this a little bit because it's going to give us slightly more useful information at times if we remember something. How many orientations of S? Well, there's only one. So that means it would take 2 electrons to fill every S. How many orientations of P? Well, there's 3. That would take 6. D would take 10 because there's 5 D's on a sublevel. So that would take a total of 10. And there's 7 F's, so that would take 14. So we're actually going to modify this just a little bit and look at it this way. 1s with 2, 2s would take 2, 2p would take 6, and so on. So notice our 3d is 10 and our 4f is 14. So written in this way, I think the Aufbau chart is a little bit more useful for some of the things we're going to end up doing. Now, how does the Aufbau chart work? Well, it just happens that it does. There's no rhyme or reason to it. It's just a memory aid. So what happens when we draw diagonal parallel arrows is it shows us what comes next. And we see that goofy thing that before we get to the 3D, we actually get to the 4S. So here's how it works. I'm going to start drawing arrows from the top. 1S is the first one I fill. That was what was at the bottom of every one of our charts. That shouldn't make anybody confused because 1S is our bottom. And then after 1S, we had the 2S. So our next parallel diagonal arrow, next we hit the 2S. Notice the next thing we hit is going to be the 2P, and then after that we hit the 3S. Once again, everything is normal so far. But when we draw that next diagonal arrow, notice we're going to hit the 3P, and then we're going to hit the 4S. So we go through the 3P And then before we get to the 3D, this shows us next comes 4s. So if we set it up in a very ordered way and draw these ordered diagonal parallel lines, we end up seeing exactly what comes next. And it hits all of the goofy things in our apartment building that is our atom. So after 4s comes 3D and then 4p and then 5s. And then after 5s comes 4D and then 5p and then 6s. And then after 6s comes 4f and then 5D and then 6p and 7f. And then next comes 5f and 6D and 7p. And at that point, we basically have run out of electrons, so we don't really worry about any more. So literally, this shows us, if we take the time to carefully write 1 through 7, 2 through 7, 3 through 7, 4 through 7, and then put in our S, P's, D's, and F's, 2s, 6s, 10s, and 14s, this is a quick, easy way we can see on the test of what comes next. So you can memorize it, or you can use an Aufbau chart. Now, this is what an Aufbau chart looks like over here on the right, and that actually matches energy per energy per energy, what Aufbau says comes next. So remember, the Aufbau chart helps us remember what comes next. Now, when describing the locations of electrons, in orbital diagrams, we're going to use arrows to represent the electrons in the orbital. So where is hydrogen's electron? Well, remember, Aufbau says we have to go to the lowest, so it's going to be the first electron in the 1s. Now, I'm going to draw that as an up arrow. You'll notice by convention, I always draw the first arrow in as an up arrow. And this deals with the fourth bit of quantum information, which is the spin. And just a fundamental, simplistic way to look at this. Now, keep in mind, we said 2 electrons can live in an orbital, and only 2. Others can visit, but they can't be stuck there 90% of their lives. Well, how come electrons which are negatively charged wouldn't be hermits, wouldn't be solitary? Because it would make sense that 2 electrons next to each other would repel. So how come we don't only put 1 electron in an orbital? Well, the idea comes from the magnetic spin quantum number. So fundamentally, if you have an electrical charge and it's moving, it has an electrical and a magnetic field. Now remember, while our electric fields may be like in charge, if we have opposite magnetic fields, we have a reason for attraction. But once we've got one of each, we're pretty much done, because now you're going to be repelling one of two, or either of the electrons on both levels after that. So that's why we have only one, or sorry, why we fill 2 electrons in an orbital. And the first one represents the positive spin, and the second one would represent the negative spin. So hydrogen only has 1 electron, so we're done. 1s with 1 arrow in it, an up arrow, we're done. So why do we need arrows? Remember, it's going to be about the spin quantum number, the fourth bit of quantum information. Now, if we had helium, we have 2 electrons. Well, where its electron's going to be? Well, by Aufbau, the first electron's going to go just where the hydrogen is. It's going to be the first one in that 1s. Now, the second electron in helium is then going to be filling that 1s. And you'll notice I put it as a down arrow down here. So I've got an up arrow and a down arrow. And that represents the both types of spin. Now, what we just looked at is what's known as the Pauli exclusion principle. At its simplest level, Pauli exclusion says the second one is going to be a down arrow because the first one was an up arrow. So the second rule of adding electrons is known as the Pauli exclusion principle, which says no 2 electrons in an atom can have the same exact quantum information. So that means their level, sublevel, shape, orientation, and spin must be unique in some way. So in the same orbital, what it really comes down to is orbitals must have opposite spin. Up and then down is how we would do it. So if we take a look at carbon and its orbital diagram, which we're going to be building to this in a second, notice these 2 electrons. Well, they're both up arrows, so the fourth bit of quantum information is the same. They both are in the same level, the 2, so that's the same. They're both in the 2p sublevel, so that's the same. But while the level, sublevel, shape, and spin are the same, you'll notice they're not in the same orientation. One's in the first, one's in the second. So those 2 electrons do have a unique set of 4 quantum information. Now, if we look at those 2 electrons, they're in the same level, the second. They're in the same orbital, shape, and orientation, but they have opposite spins. So fundamentally, Pauli exclusion principle comes down to when we put the 2 electrons in one orbital, up arrow, down arrow. That's really all Pauli exclusion says. Now, our third fundamental rule is known as Hund's law, and this deals with anything that's not an S. Notice the P's and the D's and the F's, they all do it. They have more than one orbital, and they're all at the exact same energy. So Hund's rule is when we're dealing with this situation, when we have S, P's, D's, or F's, how do we put electrons in? Because they're all at the same energy. So here's the deal. Where do I put the second electron? Well, Hund's rule says you have to put it in the next orbital over. So when filling a sublevel with multiple orbitals, remember that's all of our P's, D's, and F's, and it's equal energy orbitals, and that's what a sublevel is. Each orbital must have one electron before any orbital gets a second. And that's why in our drawing of carbon a second ago, notice this is where the fifth electron went, and that's where the sixth electron went. I didn't fill the first two P's like I did the 1s's and the 2s's. I had three orbitals here. And why would you put one in the second? Well, think about what he talked about a minute ago when we looked at why two electrons could be in one orbital. Electrons fundamentally are negatively charged things. They're going to repel each other. So if we put and cram both of them in the same orbital, that's going to be less potential energy, or a higher potential energy, less stable situation, because those electrons are going to repel each other. So technically, if we have to add lowest energy, we really need to put one in each by Hund's rule before any of them get two, because that will increase our electron-electron repulsion, and that's going to be a higher energy situation. So I know they all look at the same energy, but that's really the first one in is the same energy. So that's what Hund's rule says. Within a sublevel, you put one up in each case before any of them get two. So the sixth electron has to go in the second 2b orbital. It cannot fill the first 2p until everyone in that sublevel each had one. Then we can start filling sublevels. And by notation, we fill the first one, then the second one, then the third one. So those are our three fundamental rules of electron configurations. Everything we look at, we're going to be relying on those three rules. Now, the first is called the orbital diagram notation, or orbital notation. And you've already seen examples of that. When I stretch the different orbitals in red up the picture, those are actually showing all the different orbitals, and we were putting electrons in. Or I can just write them on the same level where you saw it a second ago. So orbital notation shows everything. It shows every occupied orbital in every sublevel with electrons. So I have to show every sublevel that has any electrons in it, the complete sublevel. And then you use arrows to show the electrons in the direction of spin. So it really does include all bits of quantum information. So carbon has 6 electrons, so the first two would fill the 1s. The second two would fill the 2s. And now I'm to a Hund's rule equal energy situation. So the fifth one would go in the first one, and by Hund's rule, the sixth one would go in the next one. So that's what carbon's orbital diagram would look like. And it shows all the information, every energy level and sublevel with electrons. It shows which orientation it's going in, and it shows spin. So we get tons of information with the orbital diagram or orbital notation. So how does this look for a slightly larger one so we can practice the idea? So we're going to draw the orbital notation of cobalt. Now the first thing we always have to figure out is how many electrons. Well, that's why Chapter 4 came before Chapter 5. One of the things we talked about in Chapter 4 is for a neutral atom, the atomic number stands for the number of protons, would also equal the number of electrons. So if you find cobalt on the periodic table, you'll see it's got 27 electrons. Now, I'm going to be putting these in orbitals, so those are the dashes. So it'd be really useful at the very beginning if I had a rough idea about how many dashes I was going to need. Well, think about it. Remember, we can only put 2 electrons in an orbital. So if I had to rough guess it, I would say if I take 27 and divide by 2, I would see approximately how many orbitals I'm going to have. Now I get 13 and a half, but I can't have an orbital, so I'm going to draw 14 dashes. So literally, draw 14 dashes across your paper. Now, you need to understand something very important here. We may not be right. This is close to how many we have. And sometimes it's right and sometimes it's not, but it's very close, and it makes what I do next a whole lot easier if I've made that guess. So don't get welded to the idea that I have to have 14. You'll see in a second. Next, we're going to label our orbitals. Now, the first orbital is the 1s, and then we go to the 2s, and so on. So rather than let it animate out, I'm going to walk through it real quick first and use my Aufbau chart. So first comes 1s. That's this one. Then next comes 2s. That's this one. And then next comes 2p. And remember how I had you do it? It was 2p6. So all the p's had 6, all the d's had 10, and all the f's had 14, and all the s's had 2. Because that's useful to know when I go to do this. So next comes the 2p, and it says 2p6. That means there's 3 of them. So don't forget. We always have 3 when we're drawing a p sublevel. After 2p, next comes 3s. So I'm going to label this one 3s. After 3s, next comes 3p, and there's once again 3p6. That means 3 of them. So 3p, 3p, 3p. Next comes 4s, and there's only 1. And then finally, I'm at my 3d, and that says 3d10. Remember, that means I have to have 5. So I count them out. 3D, 3D, that's 2. That's 3, that's 4. Wait a second. I'm supposed to have 5. So what did I need to do? I needed to add another orbital. So remember, when you're making your division guess, it's a guess. It's giving you a rough idea. But when we go to fill this one in, we didn't have enough in our 3D, so we had to add that extra one. So remember, this 14 was a rough guess. It's only when we go and use the Aufbau chart to fill in, we realize, wait, I got to show all of my 3Ds, so that means I need to put the 5th one in there. Now, next would come adding the electrons. So we're going to add following Aufbau and Hund's rule, and technically Paul exclusion principle as well, which just means up down. So first electron in cobalt goes in the 1s. Next electron fills the 1s. That's following Pauli exclusion and Aufbau. Next electron, so the 3rd one, goes in the 2s. The 4th fills the 2s. The 5th goes in the 2p. Now next we got to remember Hund's rule. Now I know we're putting in a bunch of electrons, so we're going to fill this whole sublevel, but get in the habit of always following the rules. Hund's rule says 5th and 6th should go there and 7th should go there. Draw them that way when you're filling it, and you won't make the mistake. So we're up to 2, 4, 5, 6, 7. So the 8th would go there, 9th would go there, and the 10th would fill the 2p sublevel. The 11th would go in the 3s. The 12th would fill it. The 13th would go in the 3p. The 14th by Hund's rule needs to go in the next. 15th next. 16th fills the 1st. 17th fills the 2nd. 18th fills the 3rd. 19th is going in the 4s. 20th fills it. And I've got 27 electrons, so I'm down to 7. So 21, 22, 23, 24, and 25. And that's why it's so important I remember that 5th 3D, 26, and 27. And now I'm finally done. So this is what my orbital notation or orbital diagram would look like for cobalt. It shows all of the quantum information. And yes, it's a little bit overkill in some situations, but that's why it's nice to have the next one, a way to abbreviate this and make it a little bit easier if I don't need all that information. So if I want to get rid of information about spin, and I want to get rid of information about which orientation, then I go to the next type of configuration, and that's just called the plain electron configuration. So this is our standard electron configuration. Now we're going to show each sublevel electrons with electrons in it, and we're going to use superscripts to say how many electrons are in that sublevel. So remember a second ago, this is what the orbital notation for carbon looked like. So what we're going to do differently is instead of showing all those 2p's, we're just going to show one. So the 1s has 2 electrons in it, the 2s has 2, and the 2p sublevel, it only had 2. So I put 1s2, 2s2, 2p2. Now these aren't squareds. Remember, this superscript is representing how many electrons are in that sublevel. So it's quicker. So if you had something like cobalt, it would be a lot faster to do this for cobalt than to write the full orbital notation. And that ends our first day of notes over electron configurations. Oh, no, it doesn't. We're going to do an example. So let's try one together. I forgot I included an example in here. So write the electron configuration of selenium. Notice I've got my nifty Aufbau chart here to help me. First thing I need to figure out is how many electrons. Find Se on the periodic table, and you'll see it's got 34. Now this would be bigger than cobalt, so that would be even larger to write than that if we were doing it in orbital notation, but it's not too bad in electron configuration. Now remember, we've got 34 electrons to spend, and here's where having those 2s and 6s and 10s and 14 on our Aufbau chart make it a whole lot easier. So use the Aufbau chart to add our 34 electrons. So we're starting with 34, and we're going to spend them down. So first, we've got the 1s, and that's going to take 2, so now we're at 32. After the 1s, remember how you draw the parallel diagonal arrows? Comes the 2s, and that's going to take 2, so now we're down to 30. And then the 2p, and that's going to take 6, so we're down to 24. And then next comes the 3s, so that's going to take 2, we're down to 22. And then next would come 3p, that's 6 more, we're down to 16. 4s, that's 2 more, we're down to 14. Then next comes 3d, and that's going to take 10. So now we're down to 4. Well, next comes 4p6. Now I can't just write 4p6 here because I don't have enough electrons left to write 4p6. So while I could hold a total of 6, I've only got 4 left to put in. So next comes the 4p, and it's going to hold 4. So don't just copy all the way what you see. Remember that last one. It depends on how many electrons you have left. In this case, I had 4, so I can only put 4 in that sublevel. So this is a lot faster. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Quick and easy compared to the orbital notation. And now that officially ends our first day of notes looking at electron configurations.